Hey guys, so we're back for part 2 of ice charts in chemistry here. So we looked at some basic ice charts last time, the easy kind of ones to solve where hopefully we can square root some stuff to cancel out, kind of make the math a little bit easier. We're going to look at a trickier one today. But let's start it with a little bit of theory. What is the equilibrium constant? Like, what does it actually mean? What does the number tell us? If you were to just look at the K value, what's it mean? Well, because it's a ratio between the concentration of products and concentration of reactants, remember it's always products over reactants. What does it actually tell us because of this? Well, basically what it means is if the answer to this is bigger than 1 at equilibrium, it means you should have more products. The top of your fraction has to be bigger than the bottom if it's going to be the answer is bigger than 1. So you should have more products than reactants. It means your product side of that equation is favored. We say that the forward reaction is favored. So if we have A back and forth and B, if your K value is like 50 or 300 or even like 7, any number bigger than 1, you're going to have more of the products than you do the reactants when you're done the reaction. The forward reaction, the reaction that goes that way, is favored. If Kc is less than 1, so 0.2, 1 times 10 to the negative 3, anything that's like a decimal number. If any of those are decimal numbers, it means if you were to look at this fraction here, your reactants would be bigger than your products. The bottom of the fraction would have to be a bigger number, which means we would have more reactants than products at equilibrium. We say the reverse reaction is favored. If we were to put A and B together, an equal amount of each, it would slide back until we had more A than B. So why is this important? Well, you're going to find out in just a couple minutes here, but we can use this to figure out if our answers kind of make sense. If you see a really big K value, you know you should have tons of products and very few reactants. If you have a tiny little K value, you would expect at equilibrium you should have almost all reactants and really not a lot of products. It's a way to double check your work and kind of make sure that you're on the right track. So here's an example, somewhere we might want to consider something like that. I got 0.4 moles of hydrogen gas, 0.5 moles of iodine gas placed in a 1 liter flask. All right, well, that's nice. That makes our ice chart real easy. And we're going to put this at 430 degrees Celsius, and we've got a K value. Again, K values are temperature dependent. We don't actually need to use that number. It's just there to tell us that, there is a set temperature, and that's where we got our K value from. Calculate the concentrations of H2, I2, and HI at equilibrium. All right, so we're going to be making an ice chart. I'm going to do it from scratch, and then we'll go to that one over there. So I've got H2, I2, HI, initially change equilibrium. Cool. So initially I know I've got 0.4 moles divided by my number of liters. Well, divided by 1 is still 0.4. So it's 0.4 molar hydrogen gas, 0.5 molar iodine gas, and it doesn't say anything about HI, so we're not starting with it. Another thing to check here, gas, gas, gas. Remember, if those are not gases, you don't need to include them because they're not going to have a concentration, which means their concentration can't change. So if they're not, well, I shouldn't say not gases. They can be gases. They can be aqueous. Those are the two ones that you might have to use. If it is a solid or a liquid, you don't have to bother with them, and that usually makes your math a lot easier. So just double check that. It's a quick thing to look for at the beginning. What do we need here? We need the equilibrium ones. Okay, so I start with H2 and I start with I2. And our Kc is a very big number. So this is definitely the favored reaction. I'm going to be using up some hydrogen, using up some iodine, which means I'm making some HI. Now I check my mole ratios. I'm using up H2, so I'm subtracting it. But how much? Well, 1 H2, 1 I2, and 2 HIs. 2 HIs. So whatever my change in hydrogen gas is, I'm going to have twice that much change in hydrogen iodide because of the 2 to 1 mole ratio up here. And now we know what everything is at equilibrium. All right, so my hydrogen gas will be whatever I started with minus my change. My iodine gas will be what I started with minus my change. My hydrogen iodide will be nothing. It'll just be 2 times my change. All right, so we got all these equilibrium numbers now. We would be ready to plug it into our equilibrium expression, which of course, product, concentration of HI, and of course, because there's a 2 in front, I have to square it. Products over reactants. Now remember how I said if these two are equal, you're in a good way. The math is going to be easy. That's still true, but these are not equal, which means this math is not going to be easy. So we're going to talk about that in just a minute. So I just rewrote what I did kind of on the last page there real quick, except here, down at the bottom, I plugged in my numbers. I knew the K value, the equilibrium constant's 54.3. So I plugged that one in right here. And I've got whatever my HI is up here at equilibrium. And I took, oh, that's not at equilibrium, whoops. At equilibrium, I plugged it in. And I took these two, my reactants, and I put them in down here. So you can see I can't write the bottom of this fraction as 0.4 minus x squared because it's not the same number. I have to keep them separate, which means the math is going to get a little funky. H2 and I2 are not the same. We cannot use our square root trick, which means we are now looking at a quadratic equation. For those of you that are not pre-cal buffs, a quadratic equation is anything that can be written in this form. It's got some number times an x squared term, some number times an x term, and some constant. And so what we're going to have to do is we're going to have to take that equilibrium expression. So we have to change our equilibrium expression with all of our numbers in it to look like this. We need to get 0 on one side. We need to turn it into this standard form for a quadratic equation. Once we've got it in this form, we can plug it into the quadratic formula, solve it, find an answer for x. And that's what we're looking for. We want to know what x is. That's the formula that's going to tell us. And if that looks real scary, well, we're going to talk about that. First thing, quadratic equation can have, well, 3 possible different answers. You can either get 0 solutions, which never happens in chemistry class because we're dealing with a real situation here. It's not some abstract math thing where this simply cannot be solved. This will have an answer. The only time you get 0 solutions is if this section here equals a negative number, because you cannot square root a negative number. It doesn't work unless you go into something called imaginary numbers and complex math, which again, that's all abstract math concepts. We're dealing with real physical stuff. It cannot happen in chemistry. So this should never, ever be negative. They call this section the determinant, and it should never be negative. If it is, you're going to have to go back and check some calculations. Sometimes you'll get, so that was 0 solutions. Sometimes you'll get 1 solution. Now, this is very rare, but occasionally happens when that determinant, the answer under the square root here, turns out to be 0. Because negative b plus 0 and negative b minus 0 are the same number. So you really only have one answer. It's whatever negative b is divided by 2a. Let's get rid of the squiggles. So that happens very rarely. I really wouldn't be looking for that. It's not going to be common at all. If it happens, cool, but I wouldn't expect it. This right here is what you're going to see. Because we're dealing with a very real, concrete situation. We've got concentrations. They can't be negative. They have to be positive numbers. You're going to be sorting stuff out. You're likely going to get 2 solutions, which means you need to figure out which answer is the right one, which is a mix of common sense and the Kc value. So what I mean by common sense is, let's say I get 2 values. One is 0.1 and the other answer is 12. Well, let's look here at our equilibriums. If x is 0.1, that means at equilibrium, this would be 0.3, this would be 0.4, and this would be 2 times, it would be 0.2. Those numbers make sense. What about 12? 0.4 minus 12 gives me negative 11.6. Can I have negative 11.6 as a concentration? Well, no, it's a negative number. You can't have negative concentrations. That's crazy. So that's kind of the common sense thing. Sometimes it will be very obvious because one of your answers will give you negative answers. One of your solutions will give you negative answers. That doesn't work. Sometimes they're both actually possible, but then you'll have to look at KC. In this case, KC is 54.3. We're expecting whichever answer gives us the most products. Because we know 54.3 means this reaction favors the products pretty heavily, we should be expecting a lot of products. So you should have whatever answer gives you less reactants and more products. That would be your right answer. So that's what I mean by sometimes you have to use KC. Most of the time, if you're lucky, you can use the common sense. One of these will give me a negative answer and I can't do that. Sometimes it doesn't, and you have to rely on your knowledge of what does KC actually mean. All right, so let's solve it. So here's what we do to solve this. Here's our equilibrium expression, right? I just literally stole that from right here. Same thing. Oh, one more slide. There we go. So I plug in products or reactants, write it all out the way I need to write it. First step is to FOIL it. And by FOIL, I mean I need to solve this. I do that by multiplying the first, then the outers, then the inners, and then the last ones. So my first one, 0.4 times 0.5. Well, let's rewrite this equation here. 54.3 equals 2x squared is just 4x squared. 2 squared and x squared. So the bottom we're going to FOIL here. First one, 0.4 times 0.5 gives me 0.2. My outside and my inside. So my outer ones would be 0.4 and negative x. My inside ones would be negative x and 0.5. So I have negative 0.4x and negative 0.5x, which means I have negative 0.9x in total. That was a positive 0.2. And the last ones I got negative x times negative x, which is a positive x squared. So there, I have FOILed the bottom. So that's kind of step one complete right here. Step two, remove the denominator. Fractions are evil. We don't want fractions. So to get rid of the denominator, I multiply by it. So I times this by x squared minus 0.9x plus 0.2. And I multiply the other side by that as well. So the bottom cancels out, and I am left with 54.3x squared. And then I do the second term. Where's my calculator? 54.3 times... Oh, that's 54.2. 54.3 times negative 0.9 gives me negative 48.87 x's. So that's that one done, this one done. Now this one, 0.2 times 54.3 gives me positive 10.86. So this equals, and I still have this up here because I haven't done anything with it, 4x, let's make that a nicer 4. 4x squared. Okay, we've removed the denominator. So we're getting real close now. Remember, we got to make it look like this here. So we've got no fractions, so we're getting close. All I need to do is get a 0 on one side. So step 3 up here, move everything to one side. I'm going to subtract 4x squareds. And if I subtract 4x squared there, and I subtract 4x squared there, I've got it. So I've got 0 on the one side. 4x squared and 4x squared have canceled each other out. What's left on the other side? 50.3x squareds minus 48.87x plus 10.86. All right, we did it. We are now in standard form. We can solve this now using the quadratic equation. So quadratic equation solutions, I'm going to give you guys a little tip. 3 tips, actually. How do you solve it? 1, if you are a pre-cal student or you are going into chemistry or math, you're going to want to do this by hand. And I'm going to walk through how to do this by hand right after this slide, so you'll see the full solution. If you've been an applied math student for quite a while, you've probably solved these kinds of equations using your graphing calculator, which is totally fine. Graph the equation on your calculator, find the roots. And by that, I mean like you're going to end up with a graph that looks something like this. And your answers are wherever y is 0. So wherever you cross the y-axis, whatever those x values are, those are your answers. So find those roots. Now, it's good practice to try and solve by hand, especially if you're going into chemistry or math. This is going to be a very handy math to be able to do, to be able to manipulate. It's just good practice. It'll help you. But if you're like, I'm probably not going to be going into chemistry, I just want to find the answers here, use your graphing calculator. That's fine. You can graph it, find the roots, you're good to go. And 3, my personal favorite, the last resort. I've tried doing it by hand and it didn't work. I don't know how to use a graphic calculator. I'm really stuck on this. There's no way I can figure it out. Or I did it by hand. I'm pretty sure my answer is right. I'm going to use this to check it. There are online quadratic equation solvers. So if you know you're not going to need the math skills at all, I'd say try to do it by hand, but then make sure you check it using the quadratic solver. Don't rely on this completely, but it's there to help you out. So you go to, like if you literally just Google quadratic equation solver, the first thing you get is a link to mathisfun.com, where you punch in what is your A value, what is your B value, what is your C value, and it tells you what your roots are, what your answers are, right down here. Now, you do have to have done all the manipulation of the formula that we just did. You have to get it into standard form first. So it has to look kind of like right under the solver word here. There. It has to look like that. If you don't have it in ax squared plus bx plus c equals 0, you can't plug any of the numbers in because you don't know what a, b, and c are. But once you've got it written like that, you plug it in, it tells you the answer. So in this case, our answer should be 0.668 and 0.323. There are 2 possible answers here. And if you graph it, you see why. It gives you this nice U shape here, and you can see where it crosses our axis twice. Anyways, let's solve it by hand. We'll leave this window open in the background so we can check our work afterwards. But let's solve it by hand. So, I just rewrote our formula up here. And this is the quadratic formula. Negative b plus or minus the root of b squared minus 4ac all over 2a. Real big, real scary, not that hard to actually work with. You're literally just plugging numbers in. So I need the negative. Let's start with the negative b. So what is the negative of negative 49.87? Because here's b. Well, negative is positive, so it's just 49.87. Plus or minus, that's where my 2 solutions come from. The square root of, all right, I'm going to skip some steps here. What is b squared? Well, negative b. So negative 49.87, you square it, and it gives you 2,487.0169. That is the b squared section. Do the next one in dark green here. Minus 4 times a times c. So I'm just going to write the minus. And then I'm going to do 4 times 50.3 times 10.86. 2,185.032. So that's this section. All of this over 2a. 2 times 50.3. If your answers aren't working out, 99% of the time, you got stuck with a negative sign. Like where this says negative 4ac here, a lot of times if a or c is negative, that's going to change to a positive, and if you miss that, that's a big place you might end up getting stuck. Anyways, let's continue with our solution here. I'm going to do this step next with the square root. 2,487.0169 minus 2,185.032 equals square root. Okay, so now I'm at 49.87 plus or minus, and I've already square rooted it. It's just 17.377, on and on and on and on. It's actually not on and on and on and on. Whoops. it's 7, 7, 7, 1, 2, and it goes on for quite a bit. I'm just going to save that in the memory of my calculator. Real handy to learn how to use the memory function on your calculator for stuff like this. Mine has an MS and an MR button. MS means memory store, and then you can clear it, punch whatever else you want. If you hit the MR, it's the memory recall. Just brings that one number back to mind, or back to the screen, I guess. All right, so now I have two solutions. Solution 1 is 49.87 plus 17.3 all over 100.6, which gives me 49.87 plus memory recall equals that, divided by 100.6. So solution 1 is 0.668, 4666, etc. So there's solution 1. Solution 2 is 49.87 minus 17.3 on and on and on over 100.6. So 49.87 minus memory recall equals divided by 100.6. Our second solution is 0.32, well, technically it's 29, but I'll call it 3. Let's double check. Did we get that one right? 0.668 and 0.323. Look at that. 0.668 and 0.323. Nailed it. So the question now is, I have two answers. Which one is right? 0.668 or 0.323? So pull up your ice chart again. 0.668 or 0.323. Okay. So let's find out what our answer is. Let's plug into our first one here. 0.4 minus. Well, if I subtract 0.7, roughly 0.4 minus 0.7, I'm getting a negative answer. That is impossible. I can't have a negative concentration, which means I actually have to do the 0.323. So, okay, let's do it. 0.4 minus 0.323. So it turns out H2 at equilibrium is 0.077 molar. I2 at equilibrium is 0.5 minus, we'll use this same X for everyone, minus 0.323, 0.177 molar. And HI, well, it's just 2 times X. It's 2 times 0.323. 0.646 molar. So we have basically no reactants left. We've used up almost all of them, and we've got a ton of product. Does that make sense? Yeah. Kc is way above 1. We should have a ton of product. We should have very little reactant, and you can see that we've used up most of it. We went from 0.4 to 0.07. We went from 0.5 to 0.17, and we went from nothing up to 0.64. So a huge jump for hydrogen iodide and quite a big drop for H2 and I2, which makes sense for our Kc value. So that's basically as hard as it's gonna get for equilibrium constants. Having to work through the quadratic equation is about the trickiest it is. If these numbers are the same, please use the square root method instead to save yourself from having to jump through all the hoops of solving a quadratic formula. Doing these questions, as you can tell, takes 10 minutes of jumping through the math usually and making sure things are right. And if you make a mistake, it's a nightmare to check. So that's why the quadratic equation solvers come in really handy for stuff like that. But this pretty much wraps it up. So this is your hardest equilibrium constant question you're going to have to deal with, I think. And that's it for today. So I will see you guys next time.